Donaldson today. He's here as a refugee because of the volcano. We don't know how long he'll be here. We, of course, would be very happy for ourselves if he's here long enough to give the complete series of lectures, but... You're not supposed to tell him that. But his title today, originally he had thought about giving several lectures on the same topic. In fact, his lectures tomorrow and Thursday, if he's still here, will be on a different topic. He'll be talking about scalar geometry and stability. But today he will be talking about exceptional holonomy and gauge theory.
Well, it's a pleasure to be here. I think it was probably in 1984 was my previous visit to Seiberg-Witten. So it's a great pleasure to be here, and thank you very much for this invitation to be in my family. What I'll be talking about today is, I should say, first of all, it's not going to, the talk is not going to lead to any indefinite conclusions. This is not a subject which exists as anywhere complete theory. But the reason for talking about it is I think it's an area which is quite attractive and where there's a lot of scope for work in the future. So I'm saying this just so you don't leave thinking where was the theorem after all. And it's also quite an appropriate topic for these Simon's lectures because it brings together three areas of differential geometry which one might normally think of as somewhat different, but are three which James Simons has made very important contributions to. Those being gauge theory of connections, and in particular, you see the Chern-Simons invariants. Secondly, theory of submanifolds, in particular minimal submanifolds. And thirdly, as in the title, the study of holonomy of Riemannian manifolds. So I'll begin with talking about special holonomy and recall or tell you some very standard things. This is not something I'm an expert on particularly myself. Then move on later in the talk to talk about connections with these other topics, slightly more specialized discussion. So let's recall that we have the notion of holonomy of a Riemannian manifold. We have a Levi-Civita connection which gives us a way of parallel transporting tangent vectors along paths, in particular around loops in the manifold. So if we take a tangent vector at our base point, parallel transport around this loop, it will come back to some different tangent vector. And doing that for all initial conditions gives us a map from the tangent space to itself to identify the tangent space with Rn, fix some coordinates, then what we get is out of the orthogonal group. Now, if we do that for all possible loops in our manifold, the set of holonomies, the set of these transformations that we get, defines a Lie subgroup of the orthogonal group, which is called the holonomy group of the Riemannian manifold. And it's a famous fact, which is Berger and many others, including Simons, that the possible holonomy groups are very restricted. Rather than going into that, let's just dive straight into the ones that will be of interest for us. To say one particular holonomy group, which is, can occur, is when one takes a subgroup of SO8, which can be identified itself with spin 7. So this is by definition the double cover of SO7. But this embedding doesn't have anything directly to do with the embedding of R7 in R8. This comes from what's called the spin representation of spin 7. But let's not go into spinners for the moment, because presently we'll give another more direct way of thinking of this. So we want to contemplate an 8-dimensional manifold here with a holonomy group, a very special kind of metric, which has the property that its holonomy group is this spin 7. And we can express that in various ways, various consequences. One is that we can think of the two forms as at a point, as the second exterior power of the cotangent space. We can think, if we want to be down to earth, we can think of this as antisymmetric matrices, and in turn we identify that with the Lie algebra of the orthogonal group. So we can think of the antisymmetric forms at a given point as identified with the Lie algebra of the orthogonal transformations of the tangent space of that point. But we're saying that we're supposed to have this preferred subgroup of that space. So what that would mean is we have a subspace of the two forms, which will be a copy of this Lie algebra. This is the dimension of this is of course a half times 7 times 6, which is 21. So inside our 28-dimensional exterior power, we're going to have a 21-dimensional subspace, a copy of this Lie algebra, and a 7-dimensional orthogonal complement. So this is one way of representing the algebraic consequences of having this kind of special structure. But another way, which we can, will be to say, let's take an orthonormal basis of this 7-dimensional space. Let's say alpha 1. So these things are two forms. We can take their wedge products with their wedge squares, and we can take the sum of those things. So we can set a capital omega, the sum alpha I, wedge alpha. And this is a preferred 4 form on our manifold. because, so you see, because it's an orthonormal basis, from the outer of the situation, we get the same omega, whichever orthonormal basis we choose. But in fact, if we didn't want to talk about the spin representation, we don't have to. We could just say that there's a particular class of four forms, like this, and we can think of up to conjugacy, this subgroup is just the stabilizer of any one of those special four forms. If we want to be explicit in a suitable basis, well, there are different models we can write down what these special four forms should look like, which are different models are convenient for different purposes. One will be to say, supposing we were thinking of supposing we had a manifold which actually had a complex structure, a complex Taylor structure, and in addition a complex volume form, so the holonomy actually would be SU4. And this in fact will be a subgroup of our group. We're familiar with thinking of SU4 sitting inside SO8. Actually, it would sit inside our spin 7. And then we would have a holomorphic form. Theta. We would also have a Kähler form. Omega. So in terms of the usual complex decomposition, this would have type 1,1, and this would have type 4,0. And then, in that point of view, a standard model for our omega we could take would be something like theta plus theta bar plus omega squared. So certainly, this thing is preserved by SU4. In fact, it's preserved by a larger group. That's what's here. Or we could take, if we could write our R8 as a direct sum of two subspaces, say E1 direct E2, and these are four-dimensional spaces. Let's take, say, coordinates x1 to x4 in this one, y1 to y4 in this one. Then, if we take a standard basis for the self-dual two forms in the two spaces, so let's say omega, we need to make this x0 up to x3. Omega 1 is dx0 dx1 plus dx2 dx3. Omega 2 is the same thing where we cyclically commute the 1, 2, 3. And omega primed 1 will be the same thing in the y variables. And so on. Omega prime 2 will do the same thing symmetrically. Then, from this point of view, in terms of this kind of splitting, then our model for omega we can take would be dx1, dx2, dx3. We take the volume form in each of the four plane directions. Plus the thing we can make out of the products of these two forms, so plus the sum of the omega I wedge omega prime. So this is another way of writing out a model 4 form in 8 dimensions, which is has the property that its stabilizer inside GL8 is this group spin 7, which we're interested in. So what we have, in summary, is just algebraically, if we have an 8-dimensional vector space, we have a preferred subset, A, inside its second exterior power, which we can identify with GL8R over spin 7. So we're saying the stabilizer of one of these forms is spin 7. We have this preferred space of special forms. This is just an algebraic construction. No, GL. So in fact, giving one of these forms, this is not at all obvious, actually determines preferred Euclidean structure on our 8-dimensional space. It should be. Yeah. So this means that we can. What's that? I'm just telling you here. There's well-known theory for people who work in this sort of area, but we can discuss a manifold with holonomy spin 7 in a more down-to-earth way. We don't need to talk about parallel transport or anything. What it means is that we should have, first algebraically, we should have at each point one of these special forms, and then we want this special form to be covariant constant with respect to a torsion-free connection. But actually the second property, again, we express it in a much simpler way. But all we need is this full form to be closed. So, spin 7. I neglected to look up, this is I think probably a theorem of very likely Alfred Bread. I neglected to look up exactly who it was. If and only if we have a 4-form omega, such that at each point, omega p is in this preferred subspace of our form, star, and crucially, we also want d of omega to be equal to 0. So, we don't need to talk about either spinors, or parallel transport, or connections, or anything. All we need to talk about is exterior forms, a particular algebraic condition, and the condition of being a closed form. Now this is not obvious. This is a but let's see. And we could have taken this. I mean, we could have started off. I could have started off the talk this way. I've defined this class in some way of algebra of special forms. I could just say, let's consider one of these. I mean, an 8-dimensional manifold, one of these particular 4 forms on it.
How is that defined as variant?
It's not so easy to do. To define this subset, it's not so. I don't really know a good way of doing it, apart from saying it's something which is equivalent to the standard. There's lots of ways of doing it, but I don't know a good way of doing it. like very likely experts do. It will be self-dual, or yeah, with respect to the metric which it defines. But again, it's not obvious how to define the metric. Let's see, before we finish this sort of introductory section, let's see why this statement, how this could be proved. What does this come down to? Let's just look at suppose we take a model point, only the naught, we take on, one of these particular forms. What is the tangent space? What is the A? This has got dimension this minus this, 64 minus 21, so 43. So supposing we have just a, supposing we just have a, at each point in our manifold we have a 4 form, which is a special kind. We think of choosing coordinates. And just think about the jets of the structure that we see in these coordinates. So just algebraically, by definition, we can arrange that our origin, our form is in a particular base point that we find. So omega will be omega naught plus some first order term, some of I equals 1 to 8. Say xi chi I, where chi I lie inside this tangent space of my space A. This is in some coordinates. But we could change our coordinates, and the relevant kind of change which preserves omega naught at the origin will be a second order change. So the form x tilde I is xi plus sum of ai jk xj xk. So we have freedom to change our coordinates and up to the relevant order by a tensor of this form. So in the sense of R8 tensor S2 of R8 is where this thing, because it's symmetric in these two intersections. So if we make one of these sort of jets of coordinate transformations, we'll change these things. So there's a certain map we can write down which takes this to R8 tensor this tangent space. Just given by the way we change this derivative term. On the other hand, for any such form, we can look at its exterior derivative evaluated at the origin. That only depends upon the first order term. So there's another map for this thing to lambda 5. D. And the content of this assertion is that this is an exact sequence. So if we have a form which is closed, there's a unique way to choose our coordinate system up to first order. So it's actually constant. The first order terms vanish. And those coordinate systems are another way of talking about a torsion-free connection. So saying of a torsion-free connection, precisely saying you have a way of choosing a preferred family of coordinate systems, jets of coordinate systems. So you can there's some algebra involved in checking that assertion, but you can check the dimensions. This has got dimension somewhere 56. This has got dimension 8 times 43, which is 344. This has got dimension a half times x squared times 9, which is 288. So you can see that this is not a proof, but it's at least a convincing. But this is the sum of these things. You're inclined to believe that this is an exact sequence. Therefore, that's the end of part one, telling you what all the experts know about these.
Why is there a tensor product? Why is there a tensor product?
This it? Because that's more invariantly, that's what this kind of set of coefficients represents.
The first. Okay.
Yeah. And similarly, here, this sum is. Okay, so let's not quite stop the first one here. Here I've been concentrating on 8 dimensions, but there's a similar story in 7 dimensions, which, but we can derive that one as a dimension reduction of this 8-dimensional story. So we don't need to go through the whole process again. From the point of view of groups, what we're saying is that there's a subgroup G2 contained in spin 7, which can be defined as the stabilizer of a vector under this action. So S at the 7 sphere, you can think of as the quotient is spin 7 over G2. In other words, this action of spin 7 on R8 has the property it acts transitively on the 7-dimensional sphere. We can define the exceptional Lie group G2 to be the stabilizer of our Lie preferred point. So that means if we consider, let's use the notation, let's write X8 for our 8-dimensional holonomy spin 7 manifold. If we consider the special class of X8s which have the form Y7 times R, then these things will have the property of their holonomy will be the group G2. Essentially from this, because as we said, G2 is just the thing which stabilizes the direction. Y and G2, hopefully. And if we take T to be a coordinate in the R direction, then we could write our omega in the form of phi wedge dt plus, say, sigma, where phi and sigma can be thought of as, I'm assuming, supposing this is a Riemannian product, so phi and sigma we can think of as a 3-form and a 4-form on our 7 manifold Y. Then, but not just anyone will do. The condition that, so quickly, the condition that our 4-form, this is the preferred algebraic type, can be expressed by saying that either one of phi or sigma determines a Riemannian metric, and the other one should be the Hodge star of the one you started with. So, for example, sigma is star of phi, but the star itself depends upon phi, because there's a certain Riemannian metric, which we won't quite take the time to write down, which is determined by the 3 forms of this type.
Change font, it's the same font.
Var phi, right. Right. So this is but the crucial thing is that phi and sigma should be closed forms. So if we're working in 7 dimensions, we have again we can discuss things in terms of differential forms. The condition we have is that we essentially have a harmonic form, either 3-form or 4-form, but it's harmonic with respect to a metric which itself is determined by a certain procedure, by the algebraic procedure, by the form. Then we could do the same again. I want to stop this part of the story soon. We could do the same again. We could say, let's consider the y's, which have the form z times r, where this is a 6 manifold, and look at just the same procedure. But then what we would have is that S6 is G2 over SU3. So what we would then be considering is a metric on Z6, a 6 manifold, with holonomy SU3. So these are just what are called three complex dimensional Calabi-Yau manifolds. So I guess this sort of intriguing, a very special picture that we can start with like the Calabi-Yau geometry in three complex dimensions. But we have these certain extensions up to dimensions 7 and 8, corresponding to these two exceptional holonomy groups, G2 and spin 7. But what I want to talk about is not so much. You can make this a circle, right, if you wanted to make it compact. I'm just talking about that. So there are lots of interesting questions about these manifolds. Which compact 7 manifolds admit one of these, or 8 manifolds admit these structures? But let's turn away from those questions. What we want to talk about are the geometry you can do if you're given one of these things. So let's imagine we have one of these special structures. And the interesting and attractive thing is that one can, as we said at the beginning, follow two different lines. One in the theory of gauge theory and connections, and the other in the theory of submanifolds, which are quite different kinds of geometric objects, we normally think. But the formal structure is sort of identical in the two cases. So how does that work? Because there are stories in all of these dimensions and interactions between them. We don't have time to say all that. So let's mainly talk about the 8-dimensional case, where sometimes things are similar. So let's talk about the Yang-Mills case. So this involves connections on a bundle over our manifold, but we don't really need to get into that. All that we need to know for the purpose of this talk really is that a connection is something which has got a curvature, which is a certain kind of two-form, or two-form with values in an auxiliary bundle. That was the reason for emphasizing the two forms at the beginning. So if you go back to our two forms on our 8-manifold, our 7-dimensional space plus the 21-dimensional space, then if we have a connection, there's a curvature, F, which is in two form, we can split this up correspondingly. And of course this is normal for many who are familiar with this. On the case when you have a 4-dimensional manifold, then you split up the two forms into the self-dual and anti-self-dual parts. But any time you have a way of splitting the two forms, you can do the same thing as here. And what we want to look at is the equation that the 7-dimensional part is 0. Which we might call as the instanton equation. This is a special form of the Yang-Mills equations. In fact, one can write down on a manifold with this structure.
Why are they special forms of the Yang-Mills equations?
We'll come to that just a moment. But actually, what's not? Let's just see what's crucial for us is that these are elliptic equations. So what does that mean? It means that we have the one forms, so with values in a bundle, but let's not worry about bundles. These are important because if we take two connections, they differ by a one form. So this is the variation of our connection. Then our curvature is a two form, but we're just looking at this 7-dimensional part. So we have a subspace of the two forms. And if we take linearize the equation, if we vary our connection infinitesimally, the curvature changes by a coupled exterior derivatives. So we have a the component, the exterior derivative, adding the one forms to these part of the two forms, one studies the equations up to gauge equivalence, up to the natural symmetry. So you also bring in the infinitesimal gauge transformations, which are just the functions. And the action of a gauge transformation in the connection infinitesimally is given by d. So the crucial statement, is that there's what's called an elliptic complex of this form. This is the technical fact. Again, it's easy to see the dimension. What this means, or this is what this certainly requires, is that the dimension of the bundle here is the sum of the dimension here and here, which is 8, 7, and 1s. It's saying a bit more, but more or less it's saying this is a determined set of equations. We're determining our connection has got 8 variables. We're determining 7 components of it, which is the right thing when you take account of the one-dimensional gauge invariance.
Is this classical means, or are you talking with quantum correction?
Completely classical. We're just writing down differential equations.
So if you think of omega as a map from lambda 2 to lambda 6 by wedging, like Leibniz's map, and you compare that to star, this is the actual decomposition.
That's right. That's just what we're going to. Right. That's just what we're going to say next. So there are two things we will say crucially that are good about this sort of special equation. One is an elliptic equation. The other is that we have an a priori bound, a topological bound on the dimensional energy function situation, which is just the L2 norm of the curvature, and that comes about, as Claude has just said, really from the definition of the algebra situation. If we have an alpha in that lambda 221, then it turns out that alpha wedge omega is the sign, if I went, so the sign is correct, is plus alpha squared times the volume. The other one, it would be minus. So we have what we can do is if we have an instanton, the curvature is all in this 21-dimensional piece, then the integral of the L2 norm of the curvature, we can write this as the integral of the trace of f squared wedge omega, so minus sign, and since omega is a closed form, this is a topological invariant. It's crucial that omega is closed. So this is just given by pairing the four-dimensional characteristic class of your bundle with the cohomology class of your fourth form. It certainly behaves in many ways like it's very similar to a Kähler form. It's a covariant constant form.
In the physics signature, it is sometimes called Oltonian instant. Can you remind us the connection of this?
Maybe I won't take. I mean, certainly there are many ways of developing the algebra here. One of them would be involving octonians, but that's not. I've just steered clear of that, so maybe I won't. But certainly a way of describing this would be involving octonians, as opposed to use spinors or differential forms. Yes, I would like to press on a bit. So, what the is we can write down this equation. What's interesting and very special about it is an elliptic equation, determine the elliptic equation, and we have this bound for the energy, topological bound for the energy. Just like the same fundamental structural properties that one has in four-dimensional Yang-Mills theory, when we're studying ordinary Yang-Mills instantons. It follows from this. Because, likewise, this implies well, right. Right. There's a certain index you can work out associated to this. So there's a moduli space of a certain dimension. Right. But I'm going to press on. But this is not quite what I want to be. To get to what I want to, I should press on a bit. So let's just say that we have the completely analogous formal properties for the submanifold version. And of course, Blake Lawson is in the audience. So this is an example of the notion of calibrated geometry, which was introduced by Harvey and Lawson. What we do is to consider. Oh, I just rubbed it off. Remember, we wrote down our splitting. Just rub it off just the wrong time. We wrote down this splitting. We wrote down the form in this particular version. We can consider four-dimensional subspaces of R8, which are like this one with respect to our form. So if we're given our form, we can say, consider four-dimensional subspaces, and that's decompositions, such that the form is written in the given formula. And such things, so that's a particular set of four-dimensional subspaces, and such things are called Cayley subspaces. So we have a submanifold, let's just call it Cayley, inside the Grassmannian of four planes in R8. There is, yes. So the orthogonal complement is also Cayley. And this will, well, let me just press on a bit now. So we can, if we have a four-dimensional submanifold, or eight-dimensional manifold, we can consider Cayley submanifolds, which have got the property that their tangent space is Cayley at each point. So these have the property that they're calibrated, which is to say that there's a topological bound on their four-dimensional volume. If you think back to our recipe, we have omega contained the volume form in the two variables. So if I restrict omega to this subspace, it equals the Riemannian volume. So it follows that the volume of Q, if we have such a thing, is equal to the integral over Q of omega, which, again, because this is a closed form, just depends upon the homology class of our submanifold. So this is the calibrated condition. But there are lots of things that are calibrated, like looking at complex subvarieties in general dimensions, but they're not determined by elliptic conditions. They're very overdetermined conditions. The other good thing here is an elliptic equation. So let me just say it's an elliptic equation. It'll take a few minutes to explain that in a minute. A way of saying it is that, let's just say it roughly. Oh, no, let's not say it roughly. That's what it is. Okay. So the point is that we have these basic ingredients, which are they're similar to the formal properties of four-dimensional Yang-Mills theory, but also, of course, of Gromov's theory of pseudo-holomorphic curves involving two-dimensional submanifolds is also another analogy, where we have the same property of elliptic equations and the volume is topological. Well, that's just what we're trying to get to. But then we can also dimensionally reduce these things. So we could consider a Cayley sub. Let's say the submanifold version. We could consider a Cayley submanifold inside. Supposing we have one of these cylinders, a Y7 times R. We could consider one which has got the form P times R, where P is a submanifold of Y, and the notion that we would get would then be what's called an associative submanifold of Y. P associative. Which, let's not take the time to write down the definition, we can just use that as the definition. But it's a certain, again, it has the same property. This is a calibrated condition that the volume, the three-dimensional volume, this thing is determined topologically, and it's an elliptic equation. So we get another theory in 7 dimensions, and there's a kind of Floer-type relation between the two, in the sense that we can think of, if we define a functional, define f on, let's consider, loosely speaking, all three-dimensional submanifolds of our manifold of Y. And let's define a functional, so let's picture my Y. Let's fix some base point in the homology class of interest, pi naught. Let's take another one, pi. We define a functional, possibly, by saying we're working in a fixed homology class, so we can choose a cycle, a fourth cycle, boundary one minus the other, the boundary of, say, D, to pi minus pi naught. And then we define this to be the integral of the four-form, which we call sigma, over D. But because sigma is closed, this doesn't, if we change this four-dimensional cycle by a little bit, by fixing the boundary, we wouldn't change this integral. We could change it by making a completely different choice in a different relative homology class, but this would just change this by a period. So this is a well-defined functional up to some periods, or you could say it's the derivative of this is a well-defined one form on this space of all three-dimensional submanifolds. And a way of thinking about the Cayley condition, Floer-type picture, is that formally we take the gradient flow of this functional, and that defines the condition. So if we define pi dt grad f, then we can think in a formal way of the evolution equation. A three-dimensional submanifold evolves in time, sweeps out of a four-dimensional submanifold, Cayley submanifold. And again, we can do just the same thing in the Yang-Mills case. Let me just say that. No, it's not just like in the usual Floer thing. You can't solve the initial value problem. But this equation is equivalent to the other equation. Or we could do a gauge theory version of that, in which rather than this kind of construction here, we would use the Chern-Simons invariant. So I'll just hurry through this to get on. So let's imagine that the Chern-Simons class, which is really only a global thing, is actually defined as differential form, just as notation. So there we would consider connections over our 7 manifold. We would define a functional on our connection by taking the integral over y, the Chern-Simons form, wedging in our form sigma. Slightly use of notation. But then we'd have exactly the same formula. So we'd have a functional on our space of connections whose gradient curves give our instanton equation that we were thinking about. In just the same sort of structural fashion as both as in Yang-Mills theory in 4 dimensions, and also as in Floer and Gromov type theory in symplectic manifolds and maps of surfaces. But now we can do this again because we can start with our equations on y and reduce again to a z. So there's kind of another discussion, which I'm not going to go into, for doing it all over again. So we get, rather than talks in this thing about topological field theories and things in dimension d plus 1. You consider one dimension, then you go one dimension higher as well. Here we have a sort of a 6 plus 1 plus 1 dimensional theory. At least in the formal sense, that we have all the differential geometric ingredients to write down as elliptic equations, Chern-Simons type functionals, and so forth, all the things we're familiar with, we can write down, but also in some unfamiliar aspects because of this 2 lots of dimensions. If we go right down to the Calabi-Yau case, what we get then essentially is the theory of holomorphic bundles over Calabi-Yau manifolds. So you can think of this as a kind of extra structure. You might start off with a sort of conventional kind of way, by studying holomorphic bundles over Calabi-Yau manifolds, and that's just some. Okay, so what you get when you do this dimension reduction, what you get when you go down is the condition that the curvature wedge omega squared is 0 and f0 2 is 0. This is, look at how these spaces decompose when you go to dimension. So this is the integrability condition, which means that your connection defines a holomorphic bundle. And this is the well, you do your Yang-Mills theory with a structure called G. You take GC. So this is the Hermitian Yang-Mills equation, which essentially has a unique solution for any holomorph. There's a discussion of stability. So we're coming towards the end, but we could have started a different way. We sort of went from 8 down. We could have said, let's start considering Calabi-Yau manifolds, 3 manifolds, holomorphic bundles, and complex curves. That will be the submanifold case with complex curves. But that will all be very standard and conventional. But there's some extra structure there, which you see when you go to these higher dimensional extensions. We could have done things that way. So all of this is sort of setting the scene, of course, as always, when it gets to the main point. So let me just, we've got the main points. And so the main question is there really a theory like this? That's really the question. See, we have lots of rich structures we can write down, but and we would like to, for example, let's focus on a particular question. When we're considering in 8 dimensions this Yang-Mills theory, we get moduli space of different dimensions, depending on the topology of the bundles. But if we go down to 7 dimensions, then we get the dimension reduction of that. This is analogous to looking at the Casson invariant of a 3 manifold, where we count flat connections. We always get 0-dimensional moduli spaces. So what we'd expect is this a kind of a formally somewhat similar to a Casa invariant of a manifold with holonomy G2. We have to choose a bundle over it. We would look then at connections. We'd have a condition on the curvature. The curvature condition in this G2 version would just be the wedge product with F is 0. We would like to count solutions in a suitable sense, but as one does in these kind of elliptic theories, where you count after maybe perturbing the equations in some way to achieve transversality, you need to take account of signs and so forth. But the question is, can we really do that? So what we would expect in the formal way is that we would have somewhere producing numerical invariants here, which are, they should be deformation invariants. If we vary our G2 structure a little bit, these things should change. So this is the question we're left to, is whether one can really do this.
Question? Is the gauge bundle coming from the Seiberg-Witten in type 2B? Or is it related to string theory in any way?
Well, that's what maybe you should tell me. Almost certainly, yes, almost certainly. Because this Calabi-Yau stuff, and I know it is, so I'm sure it ought to be related to string theory in some way, but I don't know. I can only see it from my own point of view. But it certainly fits in with things. I mean, in Richard Thomas's holomorphic invariants sometimes. Invariants, holomorphic bundles, which are just like Douglas has written about. So I think we should ask Mike. but I can only approach it from my... Yes. Yes. So the mathematical question is that can we do this in a rigorous way? We have the structure, and of course the difficulty is compactness, as someone astutely said. Just in an obvious sense, even if we have supposing we have a nice discrete set of these solutions, locally looking inside the space of solutions, like just what we like, we have a way of attaching signs. But if we have an infinite discrete set, how can we can't just count in this obvious sense to get a number. Or if for some particular values we have a finite set, but if in our, as we deform, so schematically this is deforming inside the space of our G2 structures, this is the space of connections, say, we might typically have just a finite number, but if as we deform some things run off to infinity and get lost, then the number we count here is different from the number we count there. And we don't have an invariant, a numerical invariant of the kind that we're considering. So I was hoping to talk about this more, but obviously I won't. But I've reached the main point to say there's a crucial and interesting analytical question that understanding compactness properties are enough of these things to be able to possibly produce numerical invariants. And just the same thing applies for these special submanifolds. You have solutions, these KB submanifolds, or the associative things, which are the reductions. If you have a sequence of those, you know there are some theorems that converge to some kind of limit in some generalized sense, but you would need to have better theorems about thinking about the notion of convergence to be able to really produce a theory like this. Just to finish, an interesting thing is that you do get this parallel story with the connections and the submanifolds. And in fact, those things is what I don't have time to talk about, but those things do become bound come together when you study this compactness question, because largely through work with Tian, and for others, but there's no case with Tian, when you follow a sequence of these connections, again, you have some kind of convergence theorem, you have convergence of a set of codimension 4, and the codimension 4 set is one of these special submanifolds, at least in a generalized sense. So when you study these compactness questions, although you might start off just thinking about connections, you're sort of inexorably led to invent the submanifold theory. You didn't know about it to begin with. So the theories really become bound up. And that fits in, we don't know how to say it precisely, but in a general way it fits in with this algebra geometric story, because this theory invented by Richard Thomas, developed by him and others, really works naturally for sheaves. So if you're an algebraic geometer, we don't talk about bundles or curves, we talk about sheaves, and everything works in that generality. The other more general kind of sheaves, in different geometry, we don't really have a way of saying that at the moment, but clearly there's something like that going on. Anyway, I should stop. I've finished my time, but I haven't really got anywhere apart from to tell you about this interesting area where it's interesting to see how things develop in the future. That's a very good question. In fact, it apparently is, but if sigma is closed, it's not due to the Bianchi identity. So, yeah, that becomes an important issue when you start to perturb the equations.
So, are there any known examples, let's say among Calabi-Gauss, where you can use a purely gauge theoretic invariant to show that two metrics of special holonomy are different components of metrics of special holonomy, where characteristic classes don't show that they're distinguished?
You mean Calabi-Gauss threefolds?
For example, Calabi-Gauss.
Morally speaking, at least, yes. If you use this algebra geometric version, which has been rigorously developed, then there are such. You can distinguish different deformation types. Not that anybody knows of, really. No. The whole theory is rather. We don't have any kind of way of generating explicit solutions. Well, certainly some of the animal issues would be relevant. Yeah, some of the animal techniques in the Ricci flow apply much more generally to other parabolic equations, including some parabolic equations that are relevant to this case. So. I'm not sure because one thing is we don't really think of these as parameterized, so it's more submanifolds rather than maps. I can't be good answer.
So if there are no more questions, let's thank our speakers. So unfortunately, the dinner tonight has been canceled, so you won't have the opportunity opportunity to ask Simon questions over dinner. Maybe you can come and test this.